Hello people, this is Week3. Today we will study image reconstruction in computed tomography as one of the Fourier analysis applications in modern medicine. Over the last 2 weeks, we discussed the basics of Fourier analysis and Fourier transform. This week, we will learn how to use Fourier analysis in computed tomography or CT scanning to reconstruct inside body images. CT scanning, as you might know, is a medical imaging technique allowing the physicians and GPs to see inside the body without cutting. It is interesting to note that the same technology is used in airport security. In CT scanning, multiple X-ray measurements are taken from different angles to produce cross-sectional images or virtual slices of a body. Then these slices are stacked to visualizing a 3D body image. For instance, in this slide on the left, we can see a virtual slice showing a cross-sectional image of a patient's chest. Any CT scan device operates by two main components: an X-ray source generating parallel X-ray beams and a row of X-ray detectors that receive the X-ray beams as raw data. As shown here, the X-ray detector is positioned on the opposite side of the X-ray generator. It's obvious that any subject, like a body, is laid down in the middle of these two. Here, we can see that the detectors receive the raw data and create a raw signal that somehow projects a body slice. We will further discuss the output signal in the following slides. As you might know, in computed tomography, the X-ray generator rotates around the body to take X-ray measurements from different angles of the body. All the raw data received by detectors are then processed to produce a cross-sectional image. In this slide, we want to further detail how computed tomography works. Suppose we have a subject like this. Consider the function fxy determines a cross-sectional image. This arrow here represents one of the X-ray beams traveling in a straight line through the subject. Here we have a raw signal, which is created based on the X-ray beams received by the detectors. This signal somehow projects a slice of the body which is at the exposure of the X-rays. There are several detectors on this row, each labeled by a number. We define the parameter R as the detector number that received the X-ray beam. In the other word, the parameter R labels a particular detector based on its offset from the center of the row of detectors. As explained in the previous slide, the X-ray scanner rotates around the subject to obtain multiple projections from different angles. For instance, the figure on the right shows a projection of the subject when the scanner rotates by theta degrees. So, the raw data or the raw signal which is collected by detectors is a set of points, where each one has an offset value r and an angle value theta. As explained in the previous slide, a set of parallel X-rays with a given angle theta projects a two-dimensional body slice to a one-dimensional raw signal. In fact, each point on the signal is equal to the strength of a ray recorded by a detector. The strength of an X-ray beam depends on the amount of the matter that the particular ray has traveled through. For instance, An X-ray beam is attenuated faster as it passes through a bone than traveling through a transparent medium. It is because the density of materials in bones is much higher than a transparent medium. So, we can obtain the strength of a beam by adding the densities of all points in the body visited by the beam. Suppose fx, y is a function determining the density of a given point x, y in the body. This sigma here calculates the strength of a beam by summing up the densities of all points in the body located on the ray. It should be mentioned, in the real applications, we don't have this density function fx, y. It's because we don't have any sectional image of the inside bodies. So, we should create the function f using the signals created by detectors. In the following slides, I will explain how to create fx, y from raw signals. As explained earlier, each X-ray beam is associated with two parameters, the offset value r and the angle value theta. Let's define a function p theta r that determines the strength of a signal with an angle of theta received by a detector number r. The value of p theta r is equal to the signal value recorded by the detector number r. In fact, for a given theta, the function p theta r converts a 2D signal into a single dimensional signal. This operation is called radon transform. This slide visualizes a sample p theta r function in form of sinogram. In other words, a sinogram graphically shows the X-ray strength measured by the CT scanner. Here, in this sinogram, the vertical axis presents theta, or the scanner angle, and the horizontal axis is r, or the detector number received the X-ray beam. Each point in the image determines the strength of a given X-ray beam with a specific theta and r values. Lighter regions in this image indicate larger function values for p theta r, while black points indicate 0. In CT scanning, the problem of image reconstruction is to find the density of the original body as a function fx, y. This 2D function is essentially a cross-sectional image that we are looking for. As explained earlier, the raw data or sinogram produced by a CT scanner is the radon transform of the human body in the form of a function p with two parameters, theta and r. Now, the question is that, can we reconstruct the unknown density function fx, y using a given p theta r function obtained from the scanner? The answer to this question is yes. We can reconstruct a density function fx, y using its radon transform. In fact, we can solve this problem using a theorem called projection slice. The correctness proof of this theorem is out of the scope of this module. However, we will learn how to employ this theorem to reconstruct a density slide fx, y from its radon transform p theta r. Okay, let's go through the details of the projection slice. Consider a given function p theta r. For any fixed value of theta, suppose p tilde theta k represent the Fourier transform of the original function p theta r. The slice theorem says that p tilde theta k is exactly the same as the value of f tilde k, l, which is the 2D Fourier transform of the density function f x, y. So, if we know p theta r function of a body for all r and theta values, we can Fourier transform the function to obtain the function f tilde. Then, if an inverse 2D Fourier transform is applied to the function f tilde, we can obtain the unknown density function f x, y. As I explained earlier, this function represents a cross-sectional image of body. In the following slides, I'm going to visually present the steps to obtain the cross-sectional image or the function f x, y. Suppose we have a sinogram of a given p theta r function. In the first step, we should Fourier transform each row of the image to obtain p tilde function. Then, as the second step, the rows in the p tilde function are rearranged as diameters of a circle as shown in this slide. You can consider this as a kind of pre-processing operation, making the data ready for further computations. Finally, we can reconstruct the image or a slice of a body by applying an inverse 2D Fourier transform to the data obtained from the previous step. But there is still one more problem. As explained earlier, we use an inverse 2D FFT to reconstruct the image. The Fourier transform is applied to p tilde theta k that is in a polar grid. However, we are looking for f x, y function in a rectangular grid. In the rest of this lecture, I will present how we can obtain a rectangular function f x, y from a polar function p theta r. In this slide, we have a series which is called back projection sum. This sigma converts original radon transform p theta r to the density function f x, y. In other words, this series reconstructs a cross-sectional image by using its sinogram. We can prove that the back projection sum can be obtained by applying some Fourier transform and mathematical interpolations. But the proof is out of the scope of this module. This slide graphically presents back projection. In fact, back projection obtains the density of an image by adding together signals for all rays that pass through a given point x and y with different theta angles. The final thing I want to discuss today is about filtering sinograms. In the previous slides, it's explained how to employ back projection sum to create the original cross-sectional image. However, pure back projection without any filtering of the sinogram p theta r usually results in blurred images. So, to get much better quality results, we have to first apply a filter to the sinogram and obtain p theta filtrate. Then the filtered sinogram is used in the back projection series to create the image. Here, I have listed the steps to obtain the filtered sinogram from P theta. First, we have to do a 1D FFT to obtain the P tilde, which is a function of k integers. Next, to apply the filter, each element in the P tilde k is multiplied by the absolute value of k. If you remember, we did this kind of filtering in lab 1. Finally, an inverse 1D FFT is applied to each row of P tilde to obtain the filtered sinogram. Here we have back projection series that uses the filtered sinogram function P theta r to reconstruct a cross-sectional image. Because of using the filtered sinogram, this series is called filtered back projection. Filtered back projection series converts filtered radon transform to a cross-sectional image. The images produced by the filtered version of back projection have better quality than the pure back projection. In Lab 3, we will implement computed tomography algorithms and use Fourier transforms to filtering sinograms. Okay, that's all for today. Thanks for watching this video.